Hello. So in this video, we are going to be tackling the quadratic formula, much loved by students, mostly hated by mathematicians, but this is a different thing. So in this video in particular, we're going to derive the quadratic formula. So you'll see sort of where it comes from, which is really that it's just sort of a quick version, as if you will, of completing the square. But we're also going to talk about arguably one of the really important parts that's within the formula, which is the discriminant. So we'll talk about that sort of once we get there. Okay. All right. So quadratic formula. So just a little bit sort of at the beginning here, the quadratic formula is used to find zeros of a quadratic, right? So in particular, that means that this thing is a formula. It should be written as the full equation. And I mention this because a lot of the times people tend to memorize the sort of hard part of it, the sort of one side of that equality. And in my experience, when I ask students what that even is, they very often have no idea what it actually is. They've just sort of memorized the pattern of letters. So it's helpful to actually remember what it is you're finding, right? So just to be clear, quadratic formula. So if you have a quadratic of this form, this ax squared plus bx plus c, and in particular, a is not 0, right? Because if a were 0, you wouldn't have a quadratic, you'd have a line. Not very interesting. So then we can have the zeros, right? That those x values as the quadratic of the quadratic can be computed by this equation, right? And that's the minus b plus or minus the square root of b squared minus 4ac all over 2a, right? That maybe you've learned a jingle or a mnemonic or something to remember this thing. But this gives you the zeros of specifically quadratics or quadratic forms, right? All right. So recall, right, remembering what zeros actually are, which is to say that zeros are the x values where in particular p of x equals 0, right, where the function, the original polynomial, equals 0. So what we're really trying to figure out is, okay, if 0 equals ax squared plus bx plus c, then what does x need to be to make that true? But it turns out that we can actually solve this. We can do it sort of, admittedly, the hard way, right? And doing it sort of abstractly is how we get the quadratic formula. But there is a way to do this without actually knowing the quadratic formula. So, for example, right, we want to figure out the zeros of this thing. I'm going to do it in generality so you actually see the quadratic formula sort of unraveling as it sort of comes to be. But I do realize that there's going to be a lot of letters here, and so you might want to pause to make sure you see where things are going or where things are coming from occasionally as we're going through this, because there's going to be sort of letter soup going on as we move forward. So the claim I made sort of earlier on is that this is really completing the square, right? So the first step of completing the square, we want to pull out that initial value. Now, since I don't actually need to worry about the a term in terms of like changing the zeros, meaning that a is a constant, so I can actually divide by that a, which is even nicer because it turns out that a is not 0, so I don't even have to worry about that possibility, right? Because we said earlier that this only applies when a is not 0. So I can just divide to get rid of it rather than keeping track with parentheses in this case because I have that equality and it equals 0, okay? So the next step is I want to take the term in front of x, here b over a, divide it in half, so it would be b over 2a, right, multiply by 1/2, and then square it, so I'd have b over 2a squared, add and subtract. That gets me this mess, right? So this is adding and subtracting that half of the middle term, that b over a divided by 2, which is b over 2a squared, add, subtract. And the whole point here is that then I can take those first three terms, right, the x squared, the b over ax, and the b over 2a squared, I can take those and collapse them down to a perfect square where it ends up being just that x plus b over 2a quantity squared. And what that leaves left over is the c over a and this negative b over 2a squared, right? So that's this part here. That's what's left over. Okay. Wow. Right, well, why? Why did I do this? Well, now I can start looking at this as I have a thing squared plus a number, where that number is admittedly a bunch of letters actually, but like these aren't variables, these are all constants. So if I actually had numbers, I could put all this stuff together and it would be like 7 or something, right? So I'd have like x plus 3 squared minus 7. And I can start unraveling that by moving stuff over and like taking a square root and that kind of thing. So that's what I'm going to do. I'm going to take those constants, which is these two terms over here. I'm going to move them to the other side. So I'm going to add b over 2a quantity squared to both sides, and I'm going to subtract c over d from both sides, which gets me sort of, yeah. So that'll get me to the next part, right? And moreover, it's sort of helpful to put these things in one big term. So I'm going to do a common denominator, and that's going to get me a denominator of 4a squared, right? And then I have to multiply by 4a on top and bottom over here. And I still just, right, that was just b over 2a squared. So that thing has already got the right denominator. So putting all that together, that gets me here. Okay. So I have the thing squared equals, again, it looks awful, admittedly, but this is effectively something like 17 or whatever, right? It's a number that's happening. So I can square root both sides. So that gets me that the square over on this side goes away. So I'm down to just x plus b over 2a. But it was a thing squared equals, not just the square root. So I'm the one introducing the square root, so I have to do that plus or minus bit. And then I'm taking the square root of that side. And I can split that square root up, right, in the top and bottom. So if I have the square root of the top, there's not really a lot I can do to make that better. But the square root of the bottom actually works out nicely because 4 is a perfect square, a squared is a perfect square. I can evaluate the bottom and get rid of, right? I can simplify the bottom to get rid of the radical, and I have just 2a in the bottom. And in fact, you probably are starting to see where, right, that part is coming into play, right? So you're looking at this, you probably are starting to see like, that looks kind of quadratic formula-y, right? So again, I'm after trying to get x by itself, so I'm going to subtract b over 2a over. So subtracting off the b over 2a, and then noticing, right, that they're both over 2a, so they have a common denominator. I can just put them together. So I'm going to have a negative b, and then I'm going to have a plus or minus square root. So that gets me my quadratic formula, right? Minus b plus or minus square root of b squared minus 4ac all over 2a. So all I really did was complete the square and then unravel it the whole way through, right? Now, looking at this, we can see that the equation actually never made any assumptions about b squared minus 4ac, right? Like, all we said was that a and b and c, they were coefficients of some polynomial. We didn't require that, for example, b is bigger than a, or that b squared minus 4ac is a positive number. Like, we never talked about any of that stuff, right? They were just coefficients, and that means that b squared minus 4ac is just whatever it is. It doesn't, we don't know, we don't have any control over that value. But it turns out that this is actually really useful because the value of that piece, right, that b squared minus 4ac, this is what we call the discriminant. And we call it that because it sort of discriminates between different groups, meaning that it sort of helps you differentiate between different situations. So this is what we're going to go to next. So I realize there's a lot of letters floating around, sort of letter soup getting through that. Everybody sort of at this level should see how the quadratic formula comes to be at least once. There you go. But take a deep breath, pause, maybe do a jumping jack or two or something, and reset, because we're going to sort of dive into the other really important part. And this is a part that you actually will potentially use quite a bit, okay? Oh, all right. Next up, the discriminant. So discriminant, really the way you want to think about this is it's some sort of distance. And in fairness, I'm using those air quotes rather liberally here. But it's some kind of distance between the vertex and the zeros of the function in the x value sort of direction, right? So horizontally, that distance. Now, to be clear, it isn't the actual distance. So if you sort of calculate the discriminant, go all the way through and get 7, you can't look at the vertex and say, it's going to be 7 to the left and right or something. It's not the actual distance, but it's a scaled version of the distance. And the important thing is that if the discriminant is positive, then the distance will be positive. If the discriminant is 0, the distance will be 0. If the discriminant is negative, well, something else is going to happen. We're going to look at that in a second. So, as mentioned, if the discriminant is positive, well, it tells you that you have a positive distance between the vertex and either one of the zeros, meaning that you can go to the right, some positive value, sort of amount, and find a 0, and then go left, another sort of positive number, and get the other x value that is one of those zeros. But the takeaway, right, is if I have to move some positive distance left or right, go to the right, some positive, go to the left, some positive, that means that I'm hitting in two different places. So when the discriminant is positive, what that tells you is that you have two distinct real valued zeros, one on either side of wherever the vertex happens to be, okay? Now, in contrast, if the discriminant happens to be 0, well, it tells you that you go 0 distance left and right to find the zeros from your vertex. But if you're going 0 distance from the vertex, you're staying at the vertex. You can go anywhere, right? So that means that both zeros are the vertex, which means that the vertex has to be on that line somewhere, right? On the x-axis somewhere. And you have two real roots, but they are duplicates, right? You have one distinct 0, and both of those roots are that 0. That's what it's telling you, okay? So with the positive one, we had two distinct roots. With 0, we have that it's one distinct root, but it's a double root, right? We have like something squared. If it's a negative, if you noticed, right, we were lifting it up. Well, same thing here. If it's a negative value, well, that means that the quote-unquote distance is imaginary. And that's because, remember, all of the discriminant, that's underneath the square root. So if we're trying to square root a negative, we're going to get some sort of imaginary value. So the distance, right, is effectively an imaginary number, which means it doesn't actually exist. It's not real, which means there are no real valued zeros. And remember, this is one of those things that from the fundamental theorem of algebra, that if we have a complex 0, then the complex conjugate is also a 0, or meaning they show up in pairs. So as soon as one of the quadratic ones is complex, the other one is as well. So it turns out both of these things, right? You have 0 zeros that are real, meaning no real zeros, 2 complex non-real zeros. Okay, so the discriminant is actually pretty useful, mostly because the discriminant can tell you sort of at a glance-ish, right? You have to calculate that b squared minus 4ac, but it can tell you very quickly how many distinct real zeros there even are, right? Which can be helpful if you're trying to do something like factor, because most of our factoring techniques, like rational root theorem, are designed to find actual sort of real valued numbers, not complex numbers. And so you can look at it and sort of immediately tell that there's not going to be any real ones, or that there are real ones and how many, that kind of thing. So again, quick recap, right? If you have that b squared minus 4ac, the discriminant being greater than 0, there's 2 real valued zeros and thus 2 real valued roots. If you have that at 0, that means that we have 1 real valued 0, which means that you have 1 root, 1 factor with multiplicity 2. We typically call these double roots or double factors. And if you have that b squared minus 4ac, if that thing is negative, then taking the square root is going to give you an imaginary number. So that tells you that there are no real valued zeros. In fact, there are must be 2 complex valued zeros that are not real. Okay. All right, so what we do? Well, we introduced the quadratic formula. We derived it from completing the square, right? Long alphabet soup thing, but just so you're aware, really the quadratic formula is just completing the square without having to go through all the steps, right? You're basically memorizing the end of the process instead of going through the process. But we also talked about sort of one of the real important parts of the quadratic formula, which is that discriminant. And that's because it's sort of one piece of it that you can usually calculate relatively quickly. That gives you a good idea of what sort of situation you're dealing with when it comes to real valued versus complex or non-real valued roots and or zeros and, for factoring and all of these things. Okay? So that is that.